In this video, we are starting section 4.1 on applied functions. So we are going to be taking all of our knowledge about functions from the previous chapter, and our goals here are we are going to try to set up a function for some quantity to be in terms of some given variable. So often when we do this, this quantity is going to be some real world quantity of interest, like maybe it'll be area or maybe it'll be revenue. And we'll talk about how we can set up an equation for those types of things. Okay, all right, so let's get right into some examples. So example 1 says, denote the radius of a circle as r. Part A asks us to express the area as a function of its circumference. So what does that mean? That means to get the area on one side, so I'll call the area A, and this might be equal to some other stuff, but I want the only variable on this right-hand side to be the circumference, and maybe I'll call the circumference C. So my end goal is to get my equation to look like that. Okay, so, well, how do we go about this? First, maybe I'll draw a picture. So I got a circle here, and I'll draw a radius, and I'll label it R. So the formula for the area of a circle, remember, that's pi r squared. Might have to think back to geometry class there, pi r squared. So this right here, I got area right now, but it's a function of r. It's a function of the radius. And in my problem, I want it to be a function of circumference. I want the variable over here to be c and not r. So it's probably going to be helpful to get a formula for the circumference. So circumference, remember, circumference is the distance all the way around a circle. So that is 2 pi r. And then let's isolate the r. So I'll divide the 2 pi over. So I get radius equals c over 2 pi. And now that I got the r isolated, I'm going to take that and plug it into my area equation. So that'll give me area equals pi. And plug it in for r, I get c over 2 pi, that whole thing getting squared. Okay, and I could simplify this a little bit. I can simplify this because if I'm dividing two things and there's a power on that whole thing, I get to distribute the power. Remember, I could distribute a power if I'm either dividing terms or multiplying terms, but I can't distribute a power if I'm adding or subtracting. Okay, so doing that, I got that pi in front. Distributing the power to the top and bottom, I get c squared over 4 pi to the 2. Okay, and now I can cancel a pi from the top and the bottom, and that'll give me area equals c squared over 4 pi. And now I got it. I got what I wanted. I got area on one side of the equation, and the only variable on the other side of the equation is c, is the circumference, and that's what this means, to get the area as a function of circumference. All right, let's look at part B. This says express the circumference in terms of the area. So now I want to do it the other way. I want c on one side of the equation by itself, and that'll be equal to some stuff. But I want the only variable on this side to end up being a. Okay, so I don't have to do all of this work again from scratch. I already have an equation to work with, but I need to now isolate c. So maybe I'll first multiply the 4 pi over to the other side. So that'll give me c squared equals 4 pi a. And then I can square root both sides. So c equals square root of 4 pi a. Normally when I square root both sides, I need to put a plus or minus. For this one, there's no plus or minus needed, because this quantity, circumference, since that circumference cannot be negative, that wouldn't make sense for that length to be negative. So my circumference is non-negative. So it wouldn't make sense to put a minus there at all. So it's just the positive root. I can simplify this a little bit more, because if I'm multiplying terms, I get to distribute that root. So that would give me like square root of 4 times square root of pi a. And square root of 4 is just 2 times root pi a. And that's what I wanted. I got circumference by itself, and it's in terms of something where the only variable on the right-hand side is the area, is a. And that's what I wanted. Okay, all right, let's take a look at another example. Before I do that, let's talk about a definition. So the demand for an item is how much of that item consumers will buy. So imagine there's some seller or some company that's selling some item, and they charge some price for it. The demand represents, well, what quantity, how much of it are people going to buy? Okay, so let's do an example. Okay, so suppose there is a linear relationship between price, which I'm going to call P, and demand, which I'll call X. At a price of $4, the demand is 12. So when they charge $4 for this thing, 12 people or 12 consumers are going to end up buying it. And each 50-cent decrease in the price results in a 1 unit increase in demand. So when they decrease the price by half a dollar or 50 cents, this means one more person ends up buying it. And I think that logically makes sense. A lower price typically means more people will end up buying it because it's cheaper. Okay, so part A says, let's express the price in terms of demand. So my goal is to get price on one side by itself, and that'll be equal to some stuff. And the only variable on this side, I want it to be demand, and the problem says call the demand X. So my end goal is to get something like that. Okay, so I'm going to start off by drawing a picture. So let's draw some axes. Okay, and so because the problem says there's a linear relationship between P and X, probably if I think about the graph here, that graph is going to have a line shape or a linear shape. So I'm going to let X still be on the X-axis, so X is my demand. X is my demand. And then P I'm going to put on the Y-axis. So P is going to be the price in dollars. P is the price in dollars. Okay, so when I form the equation here, actually, let's hold off on the equation. Let's see if we can draw some points on the line. So it says when the price is $4, that the demand is 12. So X is going to be 12. So I'll plot that point. And then it says if we decrease the price by half a dollar, so that would decrease it to $3.5, that the demand goes up by 1. So from 12 to 13. So this is another point on the graph. Okay, the graph has a linear shape, and it goes through those 2 points. So let's draw a line. Let's draw a line that goes through those 2 points. So that would be something like this. A line that goes through those 2 points. Okay, so that's my graph. And when I write down the equation, I think it's probably going to be easiest to use point-slope form because I don't have the y-intercept, but I do have a couple points on the graph. So my point-slope form, remember, is like y minus y1 equals m times x minus x1. But I don't have y as a variable here, so I won't write y minus y1. My variable instead is p, so I will write p minus p1. So I'm going to need the slope. So my slope, well, it's rise over run, where, change in y over a change in x. And I don't have y as a variable. I have p. So I'll have change in p over change in x. So how much is my price changing from my initial point to this second point? Well, the price is going down by half a dollar. So I would say negative 0.5. The negative indicates the price went down. And going from this point to this point, how much did x change? Well, x went up by 1. That's why I'm putting a plus 1. If I write this as a fraction, 0.5 is a half, so I get negative 1/2. All right. I also need to know a point. I need my x1 and my p1. So my x1 comma p1, I can use either point on the graph for that. Either one of these two. I think 12 and 4 is going to be a little nicer because it doesn't have decimals. But I could use either. So my x1 is 12, and my p1, the price is 4. All right, let's plug this stuff in. So for my equation here, I'm getting p minus p1 is 4 equals m is negative 1/2 times x minus, and then x1 is 12. Okay, so I got my equation, but remember the problem says to express the price in terms of the demand. That means I need to isolate p. So I will move the 4 over to the other side and maybe also simplify the other side by distributing the negative 1/2 to these terms. Okay, so if I do that, I get p minus 4 equals, let's distribute, negative 1/2 x plus 6 Now I'll add the 4. So I'll put an arrow. That gives me P equals negative 1/2 X, and then plus 10. And that's what I wanted. I got price by itself, and it's in terms of my demand variable, which is X. That's the only variable on the other side. Okay, and I could do a reality check on this. Like I could plug in some of my points to see, are they working out? Like if I plug in X equals 12 into this equation, what do I get? Well, P equals negative 1/2 times X times 12 plus 10. So 12 times negative 1/2, that's negative 6. Plus 10, oh, okay, and that equals 4. And that checks out because that was my price at that point. Okay, so just a little reality check there. Okay, part B says to express the revenue in terms of demand. So revenue is the total sales. So when the business or the company is selling this item, their revenue is how much total money do they get from selling that item? What are their total sales? Okay. So revenue involves two things. It involves the price, and it involves the quantity of that item that they sell, and we multiply those two things. You take the price and you multiply it by how much of it do they sell. Okay, so the quantity that they sell, well, we have another word for that. That is just the demand. The demand is how much of it consumers will buy. Okay, so let's introduce some variables. Let's call revenue capital R. For price, we've been calling that P. And quantity, which is the same thing as demand, we call that X. Okay, this is not quite what we want yet. We're not done because we want to get revenue in terms of, I want the only variable on the right to be the demand variable. I want the only variable to be X. So it might be tempting to be like, wait, can I just divide the P to get R over P equals X? Because now the only variable here is demand. Is that okay? Unfortunately, that's not what it wants because it says to express revenue in terms of other stuff, which means I need to get revenue by itself. Revenue needs to be equal to some stuff where the only variable here is X. So I don't want to have a P on the same side as R because then I don't have the revenue isolated. Okay, so how can I get rid of that P if I'm not allowed to just divide it over? Well, what I can do is I can substitute in for P because I know what P is from the previous part. I know P is this. So plugging that in, I get P is negative 1/2 X plus 10. And then I got this X is still there. So P times X. And now we got it. Now I got revenue in terms of my, just the demand variable on the other side. Okay, so if you end up taking like a business calculus class after this, you're going to see problems involving demand and revenue and things like cost and profit a bunch, which is one of the key reasons why I'm introducing you to those terms in our class, because I want you to be familiar with them kind of when you go into that next class. Even if you take a non-business calculus class, examples involving demand and revenue, they're quite common. So I think it's very helpful to go over these terms now.